The statement of Archimedes' principle we discussed is that buoyant force equals to weight of fluid displaced. So let's start with a quick example of the application of this. So we have this situation that a solid rubber, sorry, not solid, but a thick rubber shell Okay. So if density of water is 1 gram per cc, find the density of rubber. Okay, just try out this question, people. Just going through your text messages. Yeah, Durgesh, we'll discuss the test doubts in the second half of the class. Same Jagannath will discuss the HCV doubts also if you have any. This is not a new topic in fluids, Sujal. This is continuation of hydrostatics, which we have done in the first 2 lectures. It's a hollow spherical shell. Yes, Pratyush. It's not a thin shell. So that's why I said it's a hollow spherical, but it's thick. Its inner radius is R and outer radius is 2R. Yes, the outer radius is 2R. Okay. No, people, the answer is not 0.5 gram per cc. You have just blindly applied that formula. But remember, I told you that that formula, that volume of submerged part upon total volume is equal to relative density. That is applicable for a solid isotropic body. This is not a solid spherical shell. I mean, this is not a solid sphere. It's a spherical shell. Okay. Anyhow, so I'll explain it now. So this is what it looks like from the outside. See that 50% of it is submerged in water. But you have to understand one thing here, that the rubber shell itself is like this. Only this much part is rubber. So for the floating object, when we apply the principle that buoyant force balances the weight, we'll see buoyant force is density of water into volume of submerged part into G. This will be density of rubber into volume of the rubber part into G. Now the submerged part is 50% of the total volume. That's this much. Whereas the volume of rubber will be 4/3 pi into outer radius cube minus inner radius cube. So this is our relation now. Yes, Piyush, please go ahead and ask your doubt. Wow. People, I don't understand why you are struggling with some basic geometry over here. This is what the shell looks like from outside. Water has not got inside it. Okay. So when half of it is submerged, how much water it has displaced? It's displaced this much water, no? So this volume submerged is how much? It's 50% of the outer volume. That's why it's this much. Whereas how much rubber is present in that? This inner radius is R. This outer radius is 2R. This is the amount of rubber which is present. That's how much. That's this much, no? You've done center of mass, you have done gravitation. It's pretty simple. Yeah. Anyhow, hope it is clear to all of you now. Any doubts, please let me know. Okay. Let's look at another question. So a lot of questions in previous year IIT papers you will see which are based on buoyant force concept. Okay, so this is a solid metallic cylinder with a hemispherical shaped bottom surface. So basically, it's like you've taken a solid cylinder and then from that you've carved out a hemispherical surface. Okay, so this length is L and this radius is R. Now the portion of it submerged, so it is suspended under water. If the mass of the cylinder is m, then find tension in the thread as a fraction of mg, and the net force by hydrostatic pressure on the bottom surface. Again, as a fraction of mg. Okay, Rakshit, after going through this question, I'll take you back to the previous question solution once. Check out what mistake you made. I'm just taking you back to the previous question solution for a moment.
So could you just show the last sub question of the latest question? No, the latest question which you just gave now, the last sub question B.
I told you I'll just go back to it. Some
Okay.
people are seeing the previous question solution. Let them finish that. Take you back. Okay, got it. Good. Okay, so let's come back to this question. Okay, so this is also a pretty straightforward question. So there is tension acting on it. There is its own weight, but there is also a buoyant force the liquid is applying. Okay. So remember, mg will be equal to density of metal into volume into g, because it's a solid metallic cylinder. Okay. So volume will be equal to how much? It will be this much. Solid cylinder's volume minus the hemisphere cut out from the bottom, and put L equal to 6R. So this is the weight. Now likewise, you calculate the buoyant force also, and then pick up the balancing equation. It should be fairly easy from this point. Okay, so the thing is, see, I have asked for the answer as a fraction of mg, no? So you have to give the answer that way, not okay. Right. So let's check out. So see, mg is this much, okay, and buoyant force is how much? Buoyant force is equal to 4r minus 2 by 3, so that will become 16 minus 2, so 13 by 3 pi r cube into density of water into g. So now if you just take the ratio of these two, you can see buoyant force, so not 13 by 3, 14 by 3. Yeah, okay. So if you take the ratio of these two, buoyant force as a ratio of mg is 14 by 16 into density of water divided by density of metal. Okay. So buoyant force itself is equal to 7 by 72 times mg. Sorry, not 7 by 72. Density of metal is how much? 12.
So 10.
Density of the metal we've taken as how much? Density
12.
12, no? Yeah, so this is 7 by 8 into 12. So 7 by 96.
Sir, but we'll get the buoyant force as 10 by 3
10
pi
by
r cube.
3. Yes, sir.
Oh, sorry.
12 minus 2.
Correct. It's, okay. So this should come out to be 4 minus 2 by 3. So yeah, 10 by 3 pi r cube into density of water into g. Correct. Now, so this should come out to be 10 by 16 into this. So that's 5 by 8 into 1 by 12. So 5 by 96. It's okay now? Correct now? So you will get the tension as 1 minus 5 by 96 or 91 by 96 times the weight. Very
Yes.
close to the weight actually. Because yes, Aditya, your answer was correct. Correct. Okay. Okay, now what about the second part? It's almost like a trick question actually. It's very simple. As far as the second part is concerned, you know that on the cylinder, the net force due to hydrostatic pressure only is the buoyant force. So since this part is outside water, okay, there is no force due to hydrostatic pressure. So whatever force there is due to hydrostatic pressure, that is only the buoyant force, because the side walls are also straight like this. So this F only is equal to the buoyant force, which we just saw was density of water into volume of submerged part into G. Yes, so that was how much? That was 10 by
No, sir, 5 by 96.
10 by 3.
10 by 3 into pi r cube into density of water into G. So in terms of mg, yes, in terms of mg, it was equal to how much? It was 10 by 16 into density of water divided by density of metal. So this F was so this should be answer. This is what you were saying, 5 by 96. Okay. So sometimes this kind of thing becomes important. Like, for example, another version of this type of question that was asked in JEE. Okay, this is a fairly simple one, so let's do it quickly. So this time you have a cylinder which is floating, okay, and it's not, no part is cut out or anything. So it's a full solid cylinder, but it is floating in a combination of two liquids. In between the two liquids is floating like this. So this is, let's say, some oil, okay, whose density we don't know. And underneath it is water. Now this is a wooden cylinder. Okay, solid wooden cylinder, which is made of, density of the wood is 0.7 gram per cc. Now what is happening is that .8 of its length remains submerged in water. And this radius is r. So it floats in this position. So first of all, so this wooden cylinder is floating as shown. So first of all, we have to find the density of oil from this information. Secondly, if the oil layer is of thickness 0.5 R, or let's make it 0.4 L, then find the net force due to hydrostatic pressure on the bottom surface if mg is, let's say, 10 newtons. The weight of the cylinder is 10 newtons. Aditya, for the first question, you will not require mg's value. You will just get density of oil as some fraction of density of water or density of wood. You will get the relationship like that. So that is why mg was given in the end actually. You understanding, no? Whatever the size, I mean, as long as the proportions are same, no? The relationship will remain the same between these quantities. So now the question is how we will apply, Archimedes principle over here, because there's a combination of two fluids, oil and water. So one is you can just blindly apply the statement of Archimedes principle that upthrust equals to the weight of fluid displaced. Only here make it weight of oil displaced plus weight of water displaced. So that's one way of doing the question, and that will give you the correct answer also. The other way is to understand it logically, that how come the buoyant force is upwards, because you will see the buoyant force will be the difference of the downward force on the upper surface and the upward force on the lower surface. So if you apply hydrostatics principle to calculate those two forces and from that calculate the difference, you'll see you'll come to the same conclusion as statement of Archimedes principle. Okay, so this is also a good way to understand how Archimedes principle works in a situation like this. Yes, that's correct. Very good. Okay, so let's see the two different methods that we can apply to understand how buoyancy acts over here. One is we can just apply the statement of Archimedes principle. Okay, so in this case, we will equate the buoyant force with weight of fluid displaced. Okay. So that will be weight of oil displaced plus weight of water displaced. Okay. So you can see that oil is present to here, the water is present in this region. So this was 0.8 the total length. That means this was 0.2 times the total length. And this other force acting on it is mg. So buoyant force over here should be equal to density of oil into 0.2 L pi r square g plus density of water into 0.8 L pi r square g. And mg is density of wood into L into pi r square. So when we equate mg with buoyant force, you can see that we get density of wood is equal to 0.2 times density of oil plus 0.8 times density of water. So okay, so interestingly, I'm getting this as a negative quantity. Let's change the value a little bit, just a moment. Okay, let's do one thing here. Let's change this submerged. So I'll just explain why what's happening here. This will not be logically possible given this that the wood's density is only 0.7. It's not going to be logically possible. If it was made of some heavier material like ice or something, this would have been possible. So let's change this to 0.6 L. Now we'll see that is going to be logically possible. So this is 0.6 L. These values are going to change. So this is one way of understanding the Buoyant force directly from the statement of Bernoulli's, of Archimedes' principle. Okay. The other ways we can also logically understand. So the oil is applying a downward force of F1 and the water is applying an upward force of F2. Then the net buoyant force is equal to F2 minus F1. This buoyant force will be equal to so it will be this pressure difference into pi r square. Now if you take this point here as A, this point as B, and this point at C, so you can understand the pressure differences. So pressure at B, for example, is equal to pressure at A plus density of oil into G into 0.4 m, because this height difference is 0.4 m and this height difference is 0.6 m, and pressure at C is equal to pressure at B plus density of water into G into 0.6 L. You can see that pressure at C, or if we just add these two equations, so this pressure difference is actually our P2 minus P1. When you substitute this here, you will get the buoyant forces value as what we written above. So that is the whole point of this question. Okay, now for the second part, we'll change the height of the oil column also. The thickness of the oil column overall, we'll change it to 0.8 L instead of 0.4 L. Okay. So now that we have this, let's understand this part. So this depth is 0.8 L, whereas this part is 0.4 L, this part is 0.6 L. This is water. Now we want to find out this force. This is what we want to do in the second part. The force on the lower surface. The net force due to hydrostatic pressure on the bottom surface, given that mg is 10 newtons. Let's work this out. So this force is going to be equal to pressure into area, where this is the hydrostatic pressure at that point. Okay. So the net pressure at that point is atmospheric pressure plus density of oil into G into 0.8 L plus density of water into G into 0.6 L. So hydrostatic pressure at that point is this. So you can see that F is equal to
सर वो 0.4 नहीं होगा तो 0.8 ही होगा।
हम्म?
0.4 नहीं होगा
सर
लॉल।
P0 भी होएगा ना कॉमन में?
कौन सा, ये वाला पार्ट?
हाँ सर वो 0.8 का।
नहीं नहीं, देखो ना, ओपन सरफेस कहाँ पे है, ये है ना ओपन सरफेस। सो ये वाला पॉइंट ओपन सरफेस से कितने डेप्थ पे है?
ओके ओके, ये वाला।
We are not calculating the pressure difference now, no? We are calculating absolute pressure at this point. Following my point?
हाँ हाँ सर।
So this is the absolute pressure. And this is the hydrostatic pressure. That is the pressure only because of the fluid, or the gauge pressure. So this into G into L into pi r square. This is this force. Of course, there is another force like this over here, na? F prime, let's say. So the buoyant force is F minus F prime. But we're not concerned with buoyant force right now. We are concerned with this force. Now we have to find this as a fraction of mg. Na? So density of oil had come out to be 0.25. And density of water was this is coming out to be how much? 1/4 of 0.2. So that is 0.8. So that's 0.2. So it's coming out to be 0.8 times pi r square Lg. This is this force. Okay. Now we'll relate this with mg. Mg would be density of wood into volume of wood. So density of wood was 0.7. So if you relate these two, you can see F is equal to 8/7 times mg. So it should be 8/7 into 10 newtons. Okay, so please make a note of this and make sure you understand this question. Okay, so these are the types of questions and kind of logic you have to be able to apply for buoyant force. Okay. Now let's go back to pressure gradient and look at a very important case of pressure variations inside a static fluid, but this time the static fluid being at rest in a non-inertial frame. So let us look at, so this is again a fundamental aspect of hydrostatics, okay, but a more advanced aspect of it. Pressure gradient for a fluid in static equilibrium in a non-inertial frame or accelerated frame. So first case we'll see is in a vertically accelerated frame. So in this case, what happens is that the pressure gradient remains only vertical, but the value changes from minus rho g. Okay. So suppose we have this kind of situation. We have an elevator or a reference frame moving up with an acceleration a naught, and inside that frame we have got a vessel with some liquid in it. So whether we analyze this from the ground frame point of view or more conveniently from the elevator's frame, if our observer is present here, there is some fluid. So for this observer, he becomes a non-inertial observer moving with a naught.
So there will be a pseudo force, right?
So yes, we will have to consider the pseudo force. Okay. So within the fluid now, when we again consider, a vertically oriented volume element, consider this element. But now there will be a combination of two more forces acting on it, as you correctly said. Along with weight, there will also be pseudo force, which will be acting downwards. So you can see that what we'll get is minus dp into a will be equal to the sum of gravitational force plus pseudo force. Okay. So we'll get minus of del p by del y is equal to density into a naught plus g. Whereas the horizontal pressure gradient will be zero. Similarly, if we had a reference frame that is accelerated downwards like this, then inside this reference frame now the pressure gradient would have a vertical component of in this case del p by del y would be minus rho into g minus a naught, whereas horizontal pressure gradient would be zero. Okay. So this is the case of vertically
This time the
accelerated.
pseudo force will be upward.
Yes, because the pseudo force is upward, so you'll get a minus sign between
Minus,
dmg and dma naught, right?
Yes.
So the key thing here is to understand that it's like it's like the apparent weight of an object is m of g plus a naught. So that is why your vertical pressure gradient is minus rho G plus A naught.
Sir, what if A was equivalent to G? If it was free falling, the elevator.
Yes, so the pressure gradient becomes zero. Very
Yeah, so
interesting.
then the
case.
buoyant force, sir, what will happen to buoyant force then?
We'll come to buoyant force. First, understand the pressure gradient. Okay. If
Okay.
there's no pressure gradient, buoyant force is zero. So you place an object inside the liquid and then put the whole system in free fall. Na? Then the object is also coming down with G. The liquid is also coming down with G. So the object also in that reference frame, it becomes weightless. Na? Because pseudo force balances weight. And the pressure gradient also becomes zero. So neither there is buoyant force nor there is equivalent weight. Nothing is acting on the object. It will just, so in that reference frame, which is falling freely at G, it will look like the object is at rest, the liquid is at rest, but both are weightless.
Yes, they feel weightless, sir. According
Yes,
to
you understanding now?
theory.
Yeah. Whereas if your A naught is less than G, then your buoyant force will be less than the weight of liquid displaced. It will be like the apparent weight of liquid displaced. It will be density of fluid into volume of submerged part into G minus A naught, where you're falling with an acceleration A naught, but it's less than G. Got the point now? Fluid's density is rho over here. Okay. So this is the easy case. Now let's come to the more interesting case of a horizontally accelerated situation. Okay, so if we have some situation like this, now we've kept an open tank in a vehicle which is accelerated horizontally like this. So very interestingly, what we'll see is that if there is liquid in the tank, then the level of the liquid will be slanted. The surface of the liquid will be slanted like this.
Because it experiences pseudo force.
Yes, very good. Because the pseudo force is pushing the liquid back, horizontally back. So if I'm taking this as X and Y axis, you will see that because there is a horizontal pressure gradient, I mean, because there's pseudo force towards the negative X axis, so there's also pressure increasing along the negative X axis. So here mg acts downwards. So that creates a vertical pressure gradient of minus rho g. But also pseudo force acts like this.
So pressure gradient always partially differentiate.
That's why we use the partial derivative, no? Because
Yes,
it can be a
partial
function of two things, you know.
Yes, sir.
So this is the result that we'll get, and this is the easy way to remember the result also.
Yes.
However, now we'll look at the, we'll look at the derivation of this also. So within this, if you take a fluid element, now if we consider a fluid element of this type, whose thickness is dx, and this area is A, okay, and in the non-inertial frame which is traveling like this, we consider the horizontal forces only. Okay, to get the horizontal pressure gradient. Okay, so pressure into area, and pseudo force. because this one is at rest, okay, with respect to this non-inertial observer. So P is equal to pressure at x equal to x. P plus dP is pressure at x plus dx. So dP is equal to del P by del x times dx. This kind of derivation that we've seen before also. So balancing the forces, you have because the change in pressure here, let's see, this one. So we'll get the horizontal pressure gradient. There is a
So can I explain the last step? Can I explain
there
the
is a
last,
horizontal pressure gradient. Yes, tell me.
the last step, sir?
Yeah, I just substituted this. Okay, dP is substituted as, now the change in pressure is because of a displacement of dx along the horizontal direction. No? See that volume element that we have taken in the tank, it's somewhere here. So this section is at distance x. This section is at distance x plus dx.
Okay.
So,
Yes, sir.
so P is the pressure at x. P plus dP is the pressure at x equal to x plus dx. So the change in pressure is gradient into this. Okay. So the same kind of step that we had done for vertical pressure gradient earlier, same we are doing here. Got it now? So this creates the horizontal pressure gradient, and the direction is against the pseudo force.
Yes.
So it's increasing in the direction in which pressure increases in the direction in which pseudo force acts. Just like for the vertical direction, pressure increases in the direction in which gravity acts. Now, gravity is acting downwards. So as you go down, pressure increases. So pseudo force is acting along negative x-axis. So as you go along the negative x-axis, pressure increases. So just make a note of this, and then a similar derivation for the vertical one will show that along with del P by del X, there's also del P by del Y, which is minus rho G. Okay, so as I said, along with this, of course, there'll be the vertical pressure gradient also. So when you consider, so that free body diagram is more or less the same. The non-inertial frame doesn't make a difference to it because we'll consider only the vertical forces now. Now considering a volume element like this, where this thickness is dy and this area is A, and this considering only the vertical forces. It's like separately we are balancing forces along x-axis and y-axis. So this is the same derivation we have seen before. So this will give us that dP is equal to minus rho g dy. But here was so we get that same expression of vertical pressure gradient. So now using these two together, we get a unique relationship for pressure difference between any 2 points inside the fluid. So the surface of fluid will be like this, inclined. Now, if I consider any 2 points inside the fluid like this, so when I have to calculate pressure at B minus pressure at A, I have to integrate this quantity. So it is like so it's pressure gradient This becomes the formula for the pressure gradient difference. So from this, for example, we can also observe another interesting fact that if you look at the surface of the liquid, okay, as discussed earlier, it's going to be inclined. So you can find the angle of inclination on the surface. And not surprisingly, it's going to be tan inverse of A by G. So first of all, we can show that this will have a uniform slope, the surface. So why it will have a uniform slope is we can just consider a small section like this. So we can consider this point like this. So you can see that pressure difference between C and A will be equal to so pressure at C will become equal to atmospheric pressure plus rho G delta Y. Whereas pressure difference between C and B is going to be the horizontal pressure difference. So pressure at C should also be so you can see from these two equations that so delta Y by delta X is uniform and equal to G by A naught.
Sir,
Yes.
sir, what have you written besides C?
Delta Y.
Okay, C plus delta Y.
Yes. Not G plus beta. G into
Okay,
delta
C,
Y.
C. Okay, C into delta.
Pressure gradient is rho G, na? So that into delta Y is the pressure difference, no? It's a very simple thing.
Oh,
Na?
yes,
C
yes.
is below the point A.
Rho G, yes, sir. Right.
Pressure at C will be equal to how much? It will be pressure at A, which is atmospheric pressure, plus rho G into the
Plus
vertical difference, na?
Rho G
Delta Y.
delta Y. Yes, sir. Okay,
Now,
understood.
similarly, pressure at C will be equal to pressure at B. Now, pressure at B is again atmospheric pressure. It's at the open surface.
Rho G
This is how
delta
we
X.
are getting these two equations. Now,
Okay.
comparing the two equations, you can see delta Y by delta X will be uniform, okay, for this accelerated tank. So that means the surface will have a uniform slope of tan inverse of A by G. The surface at theta equal to tan inverse A naught by G in this case with respect to horizontal. So another way to understand the same thing is that if you consider these points, these 4 points. So you can see that pressure at the point 1 is equal to pressure at the point 3 is equal to atmospheric pressure. Now pressure at the point 2 can be related with this like this. And pressure at the point 4 can be related with the pressure above it at the open surface like this. So this is considering vertical pressure gradient. Okay. Now also separately, pressure at the point 2 will be pressure at the point 4 plus rho A naught G. Sorry, rho A naught into L. This is considering the horizontal pressure gradient. So now we combine these two equations. So from here we can see that so again we can see that H1 minus H2 by L, which is tan theta, is equal to A naught by G. We can suggest this. Okay, people, so hope this concept is clear over here of horizontal pressure gradient in a horizontally accelerated tank. So the very easy way to visualize this is like this, that when you have a stationary tank, it's in a stationary reference frame or in an inertial frame. So in an inertial frame, what is happening is that if you consider any object, its weight is in the vertically downward direction. Okay, so that is why the surface of liquid will be horizontal, because the surface is always perpendicular to the effective weight. So this is the direction in which effective weight is acting. Okay, and that is why there is only vertical pressure gradient and no horizontal pressure gradient. Okay. But the same thing, the moment you compare this with a situation in the accelerated but horizontally accelerated kind of situation, so you see that this changes, because now if this is moving with A naught like this, so we are in that non-inertial frame traveling with A naught like this. So then an object's effective weight becomes like this, because there is pseudo force. Okay. So you can say that the effective gravity becomes in this sort of direction. This is like the apparent weight. So that is at an angle theta like this, where theta is tan inverse of A by G. So now in this diagram, what is happening are effective gravity is in this direction. Okay. So the surface of liquid will be like this, perpendicular to this. Okay. So that's why you can see that the surface of liquid will be at the same theta. And we are taking this as x and y axis. You can see that so these two you can relate with the two components of effective weight or apparent weight. Okay, and by dividing these two, you can also see that you have okay, so at the surface this is what happens. So you can see that this vertical line of mg and horizontal surface, now your effective weight or apparent weight is inclined by theta to the original vertical line. So your surface also becomes inclined by theta to the original surface. Okay, so we will look at some specialized problems at JEE Advanced level based on buoyant force acting in a liquid in a non-inertial frame, where the horizontal pressure gradient creates a horizontal component of buoyant force also. But that's a very specialized and advanced type of question. With what we have learned in today's lecture and the problems that we have discussed, you should be able to solve H.C. Verma completely without any difficulty for hydrostatics. Okay. H.C. Verma's chapter is mixed with hydrostatics and hydrodynamics. So please do the questions of hydrostatics only from that. Okay. Also, we did not get time to discuss the questions or doubts from the major test. So we'll keep that for the next session, or you can keep sending me the doubts on WhatsApp also, or during the mentorship session also we can discuss. Okay. Many of you might be having mentorship session with me in this week. So try to discuss during that also. If anything remains, we'll discuss in the next lecture. Okay, so that's it for today's session. People, wish you all the best.
Thank you, sir. Bye, sir.
Bye, sir.
Bye, sir. Thanks.
Thank you, sir. Bye, sir.
Thank you, sir. Bye, sir.